In this video, we're going to talk about how the carbon dioxide absorbent used in our circle system helps to filter out, or I should say, absorb our CO2. And that helps us prevent any rebreathing of carbon dioxide that goes into our patient's lungs. So I'm going to label this, title this CO2 absorbents. CO2 absorbents. So I'm going to draw a quick schematic of our circle system just to show us where our CO2 absorbent is. There's going to be a more exhaustive video about how circle systems are and breathing circuits in other videos. So we have our bag, we have our APL valve, and then this is our CO2 absorbent, which I'm going to label right here. We have our fresh gas flow. Just to summarize, so we have our fresh gas flow, which carries anesthetic gas on the inspiratory side, or inspiratory limb of our breathing circuit. That fresh gas is going to enter into our patient's lungs. This is our patient. I'm going to draw him smiling. And then once our patient exhales, all this exhaled gas is going to go on the expiratory limb of our breathing circuit. Some of that gas will be scavenged and removed from the circuit. And then some of that gas, which contains carbon dioxide, will enter our carbon dioxide absorber, where it'll get absorbed, and that way that'll allow our patient to not breathe carbon dioxide or have a buildup of carbon dioxide built up in their lungs. I should mention, and just right here, that there is a one-way valve on the inspiratory side, one-way valve on the expiratory side of our circle system, just to make things complete and as accurate as possible. So there are different types of carbon dioxide absorbents that are in use today, and each of them have differing efficiencies, but the goal is the same. So the most common absorbent used today is Sodalime. All right, Sodalime here. And Sodalime contains a couple of different chemicals, and the chemistry is important. We're not going to get too much into detail about the chemistry. We're going to write down some series of reactions down, but the chemistry to understand is important at a basic level to really get a sense of how the CO2 gets absorbed in these canisters. So Sodalime contains calcium hydroxide, sodium hydroxide, and potassium hydroxide. And the way that I'm going to draw how this Sodalime canister works and all the chemistry involved is through this, depicting this diagram right here. So this is going to be our CO2 canister. We're going to have carbon dioxide come in at one end. It is going to go into this black box, which will deconstruct. And then out of it, we're going to get water and heat. So what actually happens, let's open up this black box of this canister to describe the reactions that take place. So the reaction is as follows. Our carbon dioxide enters our CO2 canister. It is going to combine with water to form H2CO3. H2CO3 is carbonic acid. That's the first reaction that takes place. So label it 1. Actually, let's do this. The second reaction that takes place is our carbonic acid, so our H2CO3, is going to combine with a strong base, in this case sodium hydroxide, in order to yield sodium carbonate which is Na2CO3 plus 2 waters, H2O, plus heat. So I'm going to label this reaction as 2. Now, one thing to note is that this second reaction, our sodium hydroxide with our carbonic acid, takes place very quickly. It's a fast reaction. I'm going to circle that. Fast reaction. So in order to not replenish stores of sodium hydroxide for the first reaction to keep occurring, the sodium carbonate product will interact with calcium hydroxide. So if you look here, just to break it down a little bit more simply, we have taken care of the carbon dioxide. There's no more CO2. So we've effectively absorbed the CO2. However, we have to replenish our stores of sodium hydroxide. We can't keep using this up. If we use it up, then our Sodalime canister will run out quicker and CO2 will not get absorbed. So we need a way to turn this sodium carbonate back into sodium hydroxide. So that's where our calcium hydroxide comes into play. So our sodium carbonate, Na2CO3, will combine with our calcium hydroxide, and that will form, let me actually just, to make it accurate, it's actually CaOH2, just given the charges and the stoichiometry. So our sodium carbonate is going to interact with our calcium hydroxide, and that is going to form sodium hydroxide. So we have our sodium hydroxide back to use in our fast reaction in order to get rid of the CO2. And then there's also going to be calcium carbonate that is going to be formed, or reformed at least. And that is reaction number 3. So this reaction here is a slower reaction. So we're able to deplete less of our Sodalime stores. We're able to consume less quickly, as if compared to if we just used this sodium hydroxide store here, or the sodium hydroxide as the main component of our Sodalime canister. So how do we know that the absorbent eventually gets exhausted? Because every now and then you're going to have to replace your carbon dioxide absorber. This reaction is not a self-sustaining cyclical reaction. We'll eventually run out of calcium hydroxide, and once we run out of calcium hydroxide, we're going to run out of sodium hydroxide, and then we're going to have a buildup of CO2. So how do we know that the absorbent is exhausted and we need to replace the absorber? The answer to that is that there's a pH indicator dye called ethyl violet. So ethyl violet. And what the ethyl violet is going to do is it's added to Sodalime, and the granule colors of the Sodalime change from white to violet as carbon dioxide builds up in the system. So I'm going to draw our CO2 canister here. These are our granules. And then as CO2 builds up, CO2, as it builds up, these granules, which are coated with this pH indicator, ethyl violet, will eventually change colors to purple. So the lower the pH, or the more acidic, the more carbon dioxide that this canister contains, the more that the reaction will take place, and the ethyl violet will go from white or the granules will go from white to violet because of the ethyl violet that's coated onto the granules. So to summarize, our CO2 absorbents, uh, the most common CO2 absorbent is Sodalime. Sodalime contains calcium hydroxide, sodium hydroxide, and potassium hydroxide. The reaction is as follows. You have carbon dioxide entering the CO2 canister, absorbent canister. It combines with water, forms carbonic acid. The carbonic acid and sodium hydroxide, a strong base, form uh, sodium carbonate, water, and heat, and that takes place as a fast reaction. And in order to replenish our stores of sodium hydroxide, in order to continue to filter out carbon dioxide, our sodium bicarbonate and our calcium hydroxide combine to form sodium hydroxide and calcium carbonate, which is a slower reaction compared to the one before. So the main products are water and heat, and this is not a totally self-sustaining reaction. Eventually, we will run out of absorbent, and the way that we tell that we ran out of absorbent is we coat these granules with ethyl violet, which will sense a pH change based on how much CO2 is built up. The granules will change from white to purple.